When a legacy microservice architecture faces a sudden surge in traffic, the entire system is vulnerable to systemic collapse. If one localized service fails to keep up with the load, the interconnected application drags the rest of the network down with it. The core flaw lies in point-to-point communication. This is located, and expect an immediate, successful response to continue functioning. We can see the mathematical problem on this node graph. 3 connected services are easy to manage, but expand this to 10 services, and the number of distinct connection paths explodes. The architecture devolves into an unmaintainable web of intersecting dependencies. Because these dependencies are tightly coupled, a slowdown in a single location becomes a network-wide crisis. If a downstream service experiences a memory leak and slows to a crawl, the upstream services waiting for its response also stall, causing traffic backups that propagate backward across the entire network. An enterprise system cannot scale to handle millions of users if its data routing relies on rigid, synchronous service-to-service dependencies. The architecture requires a mechanism to break those direct links. To solve the tightly coupled network problem, the tech industry standardized around an open-source technology developed by the Apache Software Foundation, Apache Kafka. Kafka operates as a distributed, fault-tolerant stream processing platform. It moves beyond the limitations of simple message queues to manage high-throughput data feeds across thousands of servers. Mastering Kafka is a core requirement for modern data engineering. It is a technology our team at Royal Research analyzes closely as we evaluate the infrastructure of today's leading technology firms. To understand how companies process billions of daily interactions without crashing, we have to tear down Kafka's architecture from first principles. We need to see exactly how it replaces rigid databases with a continuous, real-time central nervous system. Kafka serves as a messaging backbone. A producer drops an event into a scrolling track called the Kafka ledger immediately, without waiting for a response. On the side, consumers plug in, pulling events independently at their own processing speeds. By placing this decoupled communication layer in the middle, a single online checkout event can be broadcast to dozens of different services simultaneously. Crucially, adding a new consumer service adds 0 computational load to the checkout service itself. This hub-and-spoke model completely eliminates direct dependencies. Engineering teams can scale services, update them on the fly, or completely restart individual microservices without interrupting the data flow or affecting the uptime of the broader application. Traditional relational databases store the current state of a system, but Kafka operates on a different principle. This split-screen diagram highlights the difference. On the left, a traditional database deletes and overwrites the old balance value. On the right, Kafka utilizes event sourcing. State changes are strictly append-only and immutable. New events simply append to the leading edge. This provides significant system resilience. If a consumer microservice crashes and loses its internal memory, the data remains safe in the log. Upon rebooting, the service connects to Kafka, reads the immutable log from the exact point it crashed, and sequentially processes the events to perfectly reconstruct its current state. Treating data as an immutable stream of historical events, rather than overwriting a static snapshot, creates an uncorruptible source of truth and allows systems to recover seamlessly from failure. While a central ledger solves software dependencies, it introduces a physical hardware problem. If all enterprise data flows through a single machine, that machine becomes a physical bandwidth bottleneck and a single point of failure. To scale, Kafka distributes data across multiple servers, or brokers. The ledger splits into parallel partitions across distinct racks, parallelizing ingestion. Using a replication factor, partitions are automatically backed up to adjacent brokers. If a broker fails, traffic instantly reroutes to surviving replicas. The combination of partitioning for ingestion speed and replication for data safety forms the architecture that allows global enterprise systems to operate with 0 downtime. We can see this distributed architecture operating in high-demand environments, such as the streaming infrastructure at Netflix. Netflix routes billions of messages through Kafka every single day. They utilize this exact partition framework to monitor global infrastructure health in real time and to calculate personalized content recommendations with low latency, processing behavioral events the moment a user clicks their remote. The required throughput is equally high in the Internet of Things, where thousands of remote edge devices broadcast telemetry data simultaneously. Automotive manufacturers use Kafka to manage connected fleets. A single autonomous vehicle streams relentless GPS coordinates, engine diagnostic logs, and edge computing calculations back to central servers. Whether aggregating application logs for a streaming service or ingesting vast swaths of telemetry from vehicles on the highway, Kafka's distributed design ensures that the volume of concurrent connections does not overwhelm the ingestion pipeline. This capability enables event-driven architecture, or EDA. In an event-driven system, the fundamental unit of data is the event itself, a user click, a sensor spike, or a trade execution. When that event is published, it triggers immediate, automated reactions across the entire software ecosystem. The high-stakes proving ground for event-driven architectures is the financial sector, specifically stock exchanges and global trading platforms. This diagram shows a financial data stream. Processing millions of financial transactions per second requires a system that delivers near-zero latency without sacrificing reliability. High-speed data blocks representing trade ticks enter Kafka, instantly triggering downstream services like risk management. Streaming real-time market data through Kafka allows automated algorithms to execute trades, detect fraudulent anomalies, and reassess portfolio risk the exact millisecond a market event occurs. In finance, stale data is identical to wrong data. By guaranteeing that information is processed and delivered the moment it is generated, Kafka ensures market integrity and keeps automated systems operating in the present tense. Beyond routing transactions, Kafka serves as the primary funnel for continuous analytics. It integrates natively with downstream stream processing engines like Apache Spark or Apache Flink, allowing organizations to analyze data while it is still in motion. Retail companies use these integrations to fan out point-of-sale and mobile app data into real-time dashboards. This continuous flow allows them to optimize local store inventory and adapt marketing strategies continuously throughout the day, rather than waiting for an overnight batch job. By replacing brittle, tangled microservice dependencies and sluggish database batch jobs with a unified, distributed ledger, organizations solve the n-squared complexity problem. Decoupling communication allows independent engineering teams to scale. Replicating partitions guarantees data safety. And treating all data as a continuous, immutable event stream means software can finally react to reality as it happens. In the modern data engineering landscape, Apache Kafka provides the fundamental circulatory system required to build, scale, and maintain a resilient digital enterprise. We thank Royal Research for their insights into these mission-critical systems.